In the last video, we discussed simple harmonic motion. What we did was we essentially looked at a mass on a spring that if it gets with spring constant K, that if it gets pulled to the side or kicked or given some bit of motion, it oscillates back and forth about its equilibrium position. We looked at this and we saw that Newton's second law, F equals ma, could be rewritten according to Hooke's law with K negative kx, the force on the mass due to the spring, is equal to mass times the second derivative of the position with respect to time. And rearranging that, we got our equation that the second derivative with respect to time of the position was equal to negative k over m times the position as a function of time. And when we looked at this, what we realized was eventually by the end of the video that solving for that equation gave us the position of that mass as a function of time was equal to some amplitude a times cosine omega t minus something we call the phase constant. And this is how we describe simple harmonic motion, motion that repeats itself and follows a sort of sinusoidal pattern. And for the mass on the spring case, we showed that omega, that angular frequency, was equal to the square root of the spring constant over the mass. We also compared this to uniform circular motion. If I have an object that goes in a circle with a constant angular velocity, and I think about the x position of that object going in that circle, that position can be described the exact same way, a cosine omega t minus phi naught, where phi naught, that phase constant, is the initial angle that it's at, and it just spins around and changes its angle. Delta theta is equal to omega times t. So we can see how simple harmonic motion is exactly mapped to uniform circular motion. Today what we're going to do is we're going to look at another example of simple harmonic motion that's a really common one, and see that it as well, like all simple harmonic motion, can be described using this cosine equation. This phase shifted cosine is what we would call it. So let's look at the pendulum, right? A pendulum is basically just some mass hanging at the end of some stiff string or wire or something. And it's, we've seen this before, going to swing back and forth along that arc length there. And we can analyze this sort of the same way we did the mass on the spring, or the same way we've done things with dynamics the entire, since we first learned Newton's laws. So we have our mass m, and what are the forces acting on it? Well, there's some tension going up on the wire towards the pivot, and there's the force of gravity pointed straight down towards the center of the earth, mg, right? And we're going to pick a coordinate system to describe this in. And our standard sort of coordinate system we use, because this is essentially moving in a circular path, would be that RTZ one. So we have an R direction and an R direction and a tangential direction like this. And if we look at Newton's second law, we can analyze this in that coordinate system, and we get F net is equal to mass times acceleration. And if we do that in the radial direction, what do we get? Well, in the radial direction, we have tension in the positive direction, and we have this t component of gravity, which is mg cosine of that angle theta, right? So this is going to be minus mg cosine theta, and it's going to be equal to mass times v squared over r, which is L, which is just the radial acceleration in that. That's all well and good, but what we're really interested in is its motion in that tangential direction. So if we look at the tangential direction of motion, we're going to have, again, the net force in that tangential direction is equal to mass times acceleration in that tangential direction. And what we get when we get that is, well, the tension component has no, or the tension has no component in the radial direction. All we have is this gravitational sort of component, uh, mg sine theta, that's in the negative t component. So the net force is negative mg sine of that angle, and it's equal to mass times acceleration in that tangential direction. Now, just like we did with the mass on a spring, we can write that acceleration as mass times the second derivative with respect to time of the position in that tangential direction, right? And that tangential direction is just s. So it's the second derivative of the position along that arc length, s. And that's equal to negative mg sine theta. Now, we can think about how we describe angles in terms of radians, right? And if I have some arc length s and I'm at some radius r, that theta, these are related, theta in terms of radians is equal to s divided by r, or s is equal to r theta, right? So if I take the derivative of s with respect to time, since I'm staying at a constant radius, this is just going to be r d theta dt. And if I take the second derivative of that position along the arc length with respect to time, that's going to be r times the second derivative of theta with respect to time. So I can make that substitution in Newton's law here. And that gives me negative mg sine theta is equal to m times r, which in this case is just the length of that string, so ml times the second derivative with respect to theta, or the second derivative of theta with respect to time. Doing a little bit of algebra, these masses cancel, and we have negative g over L sine theta is equal to the second derivative with respect to time of that position. Now, so this is what Newton's second law gives us for the tangential direction of this mass hanging from a string. We can do one more thing with this, and it has to do with the angle theta, right? If we think about most pendulums and how we swing them, we're normally not, swinging them very far around like that. If you think of a grandfather clock or something like that, we have the mass, barely comes out. It doesn't come out too far away from the vertical, i.e., it's at small angles. And when we think about this sine function here, well, if we were to plot sine x of x, right? So we have sine of x as a function of x, it looks like this, right? And if we look at where x is very small, in that region, we essentially have a straight line, right? When we're really close to the origin there, which essentially means that that sine of x is approximately equal to x. It's got a slope of 1 and it intercepts 0, so that's our y equals mx plus b. Another way we can think about that is you may recall that sine x can be Taylor expanded or written as x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot 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 dot, and keep following that pattern. If we think about where x is very small, then if x is less than 1, really, x cubed is going to be much less than 1, and then x to the 5th is even going to be smaller, and all of these higher order terms become less and less important. They get smaller and smaller, not only because the exponents making the x term go very small, but the denominator in those fractions are getting small as well. So for very small x, we can essentially ignore those because they don't really change much, and we have this same small angle approximation there. So if we make that small angle approximation in our Newton's second law equation, what does it give us? Well, we end up with negative g over L, but we substitute just theta for that sine theta, and that is equal to the second derivative of theta with respect to time. So this is what Newton's second law gives us in terms of our angle theta of that pendulum when it's at small angles. Now, we can compare this to what we saw with the mass on a spring. If you remember what Newton's second law gave us in that case, it was negative k over m times x was equal to the second derivative of x with respect to time. These two mathematical equations, these what we call differential equations, are identical. We have the variable, the function we're trying to solve for, times some negative constant is equal to its second derivative. Over here we have the same thing. The variable, the theta as a function of time we're trying to solve for is equal to times some negative constant is equal to its second derivative with respect to time. Graph that 2 there, right? So mathematically these are identical equations, so we know that the solution, that theta as a function of time, is going to have the exact same form our x as a function of time did, which is a cosine omega t minus phi naught, right? And that's how we can describe the angular position of our pendulum as a function of time. One difference is, in this case, in the mass on a spring case we went over in the last video, the omega was the square root of that constant that's multiplied by our x in that equation. In this case, that constant's different, so our omega is going to be equal to the square root of g over L in this case. And there is how we describe our pendulum. The angular position is a cosine omega t minus phi naught with the angular velocity equal to the square root of g over L. Interesting thing about, kind of unexpected perhaps, is that angular velocity or that angular frequency does not depend at all on mass. All it has to do with is the force of gravity and the length of the pendulum, which kind of makes sense because the strength of the force that's causing it to oscillate, if we think back to our Newton's second law, the strength of the force that's causing it to oscillate depends on mass, but that's also determines how fast, how much acceleration there is in that, and they end up canceling in such a way that the mass does not matter when it comes into this simple harmonic motion. We could also write this in terms of the arc length. If you think back to our pendulum here, we're describing this currently in terms of the angular position theta. We could describe this motion in terms of the arc length s, or position along that tangential direction. All we'd have to do is use our relationship between that arc length and our angular position. So we can just multiply both sides of this equation by r and get our position along the tangential direction in terms of with respect to time. And what essentially that is, it's going to have the same form, a cosine omega t minus phi naught, but this amplitude is going to be different than the amplitude in the angular position. So the amplitude in this case is the maximum displacement along along s, the s direction, and in this case, this amplitude is the maximum displacement along theta. So that would be theta max. This would be s max. So that's probably the best way to write this. S of t is s max times very sloppy cosine omega t minus phi naught, and theta as a function of t is equal to theta max cosine omega t minus phi naught. And again, just to reiterate, in both cases, that angular frequency is the square root of g over L. And that's how we can describe a pendulum. Extremely similar or analogous to the simple harmonic motion of a mass on a spring, and pretty common thing in introductory physics. The last thing I want to bring up in terms of simple harmonic motion is the idea of damping, right? So we're all probably very familiar with that. If I take a pendulum, for example, in our in what we've covered today, and I pull it off to the side to some theta max, and then release it, and it swings back and forth, that doesn't go on forever, right? Eventually, it is going to come to a stop. It's going to slow down. It's not going to swing out as far and eventually stop, right? If we were to sort of plot, you know, that theta as a function of time, well, I'd start up here with the maximum amplitude I release from. It'd start to oscillate back and forth, but those oscillations would get smaller and smaller and smaller. And I'd expect something like that just from experience, still oscillating back and forth, but not quite as far and slowly slowed down, right? And this is due to some, damping, just as we might expect. There's friction, there's air resistance, there's a bunch of things that are converting these macroscopic energies into thermal energy or other types of energy. I mean, if you were to think of the potential energy in this pendulum, right, it's changing height as it goes back and forth. So when it's at its maximum amplitude, that's at its maximum. Its total energy is in its gravitational potential energy, and then the next time it comes back, it's got a little less and a little less, and that starts to decay or get less and less. So we can actually look at this and try to analyze the more realistic case where there is some damping on these harmonic oscillators. Another example of a damped oscillator is if you think about your car's suspension, right? If you drive over a bump or something, you start to bounce up and down the car, but it stops pretty quickly. It doesn't keep bouncing the whole way up the highway or anything like that. Now, the process of that damping can be pretty complicated. You can have intentional dampers in there. The form that it can take can be a little more complicated, but a typical simple model we can apply to this is similar to our drag force. We just have some linear damping that's proportional to how fast that oscillator is moving back and forth. In that case, there'd be some force that's proportional, that equals negative some constant b times how fast it's going. If we include that in our Newton's second law, it changes a lot of things. Now, the math behind it is a little beyond the scope of this course, but if we have, our mass on a spring that has the force of the spring pulling it back, but it also has that drag force opposite the direction of its velocity, we get a different solution for our position as a function of time. And it looks like this, where we have some maximum amplitude, but it's got this exponential term where the exponent is proportional to sort of the strength of that damping force, and times time divided by 2 times mass. And it has a similar sort of cosine term in the argument here, cosine omega t plus phi, or phi naught. Now, in this case, the omega naught is the omega is actually equal to a modified angular frequency. So previously we had, when in the undamped case, the angular frequency is just square root the spring constant over mass. In this damped case, it's square root the spring constant over the mass minus this term here that has to, again, do with the strength of the damping term, that b squared over 2m. So the angular frequency goes down a bit. And that sort of makes sense if you think about it qualitatively. This object's going back and forth, but there's some force that's causing it to not quite accelerate as much because it's always in opposite the direction it's going. So it's going to take longer to do that. It's going to be the frequency. It's going to happen less times, less per second, I guess, fewer oscillations per second. And we get rid of that damping force. We make b equal to 0. We end up with the same angular frequency that we had in the undamped case, which makes sense. But what does this look like? Well, graphically, it's exactly what we expected. We started with some amplitude of oscillations. They're going to oscillate like this back and forth, but they're going to get smaller and smaller. And that initial amplitude A decays as due to that exponential term there. The amplitude is going to slowly get smaller and smaller with time. So we can actually sort of rewrite that equation in terms of that exponential term out front, we can describe it as a maximum amplitude that just gets smaller with time. So, like in this case, and then our equation for that damped harmonic motion looks similar to what it was for the undamped case. We just have a time-dependent maximum um, displacement. And that maximum displacement, again, depends on the strength of that damping force. And the stronger the force or the larger the B, the quicker that amplitude decays back towards zero and stops. Now, this is an example of exponential decay, which is ubiquitous in science. There's tons of things that decay in that way. And essentially, you have some quantity, in this case, call it U, that has some initial conditions, some initial amount of whatever it is, in this case, displacement uh, or energy. In other cases, it might be the number of a certain isotope that is decaying, and it's going to have an exponent with some exponential dependence that has some negative exponent proportional to some constant v naught. So it's going to, in our case, it was a time constant. So we had e to the negative. All those constants had units of inverse time times time, and after one of those constants, that quantity has decayed to 33% of its initial value. After two time constants, it's 13%, and so on and so forth. And you can look at sort of how long it takes to decay back down to zero, and it's all of that is really captured in whatever that decay constant is, that constant term in the exponent of that function. In these simple harmonic oscillators, we typically think of energy as being what's decaying. So if we think of the total energy in that system, when it's at its maximum amplitude, it is just dependent on the potential energy, which is 1/2 kx squared for a spring. So it would be the energy goes as 1/2 k, the maximum amplitude squared. And that maximum amplitude decays as a function of time. When we include the squaring and go through all this algebra, we can write the energy as a function of time as some initial energy in our system, e to the negative t over tau, where that tau is the time constant. And it is essentially how long it takes for the energy in the system to decay to about 37% of its initial value. And if we look at all the equations and do all that algebra, that tau ends up being equal to the mass divided by that B term that was proportional to essentially the strength of that drag term in that drag force. And so it's just a really nice example of exponential decay, which you'll see in a lot of other courses and in science in general. So that's what we've got. We've gone through simple harmonic motion. They're described by that phase shifted cosine term. We looked at mass on a spring examples where that angular frequency is the square root of the spring constant over the mass. For a simple pendulum at small angles, that angular frequency goes as the square root of g divided by the length of the pendulum. But in general, we describe them using that same equation, that same equation where our displacement is going to be some amplitude cosine omega t minus that phase constant. And that's how we describe simple harmonic motion. If we want to describe a damped case, it's the same thing, except for we have a slightly modified omega, and our amplitude depends on time. And then we get this exponentially decaying amplitude and exponentially decaying energy. We'll work on this more in the synchronous sessions, go through some examples. If you have any questions, feel free to reach out and email me, and we can hopefully help get to the bottom of it.